Perfect. Okay. So hello, everyone. My name is Mohammed Ghazmala. I'm the AI task force lead here at King's Distributed. We basically do distributed compute and manage the distributed computer protocol, which is, as Ian mentions, the most powerful web-based distributed computer that I'm aware of. I'm here as the AI task force lead. And basically, my job is to work on the distributed compute AI stack and make machine learning and artificial intelligence inferencing and training as easy as possible for folks using the distributed compute protocol. If I ever mention DCP at all, that's basically just me saying distributed computer. If I mention anything that starts with DC, you can basically just say DC is distributed computer. So I'm going to go ahead and give a little bit of an introduction to myself so that you know a little bit about me. And then I'll hop into, so long as Dan isn't here, some more AI-based demos. But let's get on with that. So about me. I'm actually a Queen's University Master of Computer Science alum. I actually started off at Queen's for biochemistry in my undergrad. And I realized very quickly that that's not about me. I'm not about that life. And I realized that I actually really wanted to do game design. And the aspects of game design that really, inspired me were the aspects of artificial intelligence and specifically pathfinding, A-star, Dijkstra's, and all those interesting algorithms. And as I found myself delving into game design and artificial intelligence in games, I started to get, into computer vision. Computer vision was one of my passions for quite a long time. And the field of computer vision has changed a lot in the past few years. And mainly this is due to the advancements in machine learning, neural networks, and artificial intelligence. And naturally, as I grew to do more computer vision projects, I also grew to do more and more neural networks and ML-based projects. So my undergraduate thesis was actually on, if you notice this image on the bottom right, was actually on, you may have heard of YOLO, You Only Look Once, a computer vision-based object detector. I took a series of frames from a video and I predicted where objects would be in the next sequence of frames. So essentially it was a predictive video object detector based off of the You Only Look Once framework. In my master's, I did a few other projects. So on the left here is my Hong-based multiple models, time delay reinforcement learning artificial intelligence system. So on the top there is your typical Q-learning approach for reinforcement learning with Hong, but on the bottom right is, or on the bottom, sorry, is the multiple models version, which actually includes some ideas, some preconceptions of rewards in the future based off of current actions. So it's a little bit smarter in how it approaches the game. And on the right there are some video of my master's thesis, which was in smoothness, specifically on video object detection. So looking at smoothing video object detectors and the frames that they produce from it. A lot of this, it seems, was very interesting for the DRDC. And so a lot of my work was through contracts with the DRDC and RMC, as well as through Queen's University. And, I ended up defending my thesis and successfully graduating, so that was really nice. This was actually just a few months ago, so I'm pretty happy about that. But let's move on. What about now? What do I do now? As soon as I graduated, actually, I started doing work for DCP and DCL, the Distributed Compute Interface. And mainly the reason I'm interested in that, and the reason I hopped on board so quickly, is that I was so interested in this idea of distributed compute. It's an idea that's, we can abstract it away and use a whole bunch of supercomputers that we pay a lot of money for and try to distribute out our workloads through. But there's a lot of stuff that you have to do to make that work, a lot of managing of the systems, a lot of managing of the dependencies. And DCP really makes that easy. So my job at the AI Task Force is to delve into this novel field of distributed machine learning and the distributed machine learning stack on DCP. This gives us a whole bunch of new problems. There's a whole set of new problems with If you've tried to train a network at all, you'll know that there's this concept of gradients that help us improve our network, basically. And as there are, different networks being trained on different computers, they may have different gradients, and being able to accumulate those gradients in different manners is an interesting problem with a lot of research applications that end up being quite interesting, but also quite difficult. But this is a field that is getting more and more popular. As many of you may have heard of OpenAI's GPT-2 model, as well as OpenAI's GPT-3 model. These distributed techniques are actually one of the only ways we can really train those models nowadays, because those models are so large in terms of memory and in terms of size and in terms of compute needs that they have to be separated out either on more GPUs or more machines in such a manner that makes it quite difficult to be able to just train it on one machine. And so you have to use these different techniques to be able to train your ML models on multiple machines. And OpenAI's GPT-2 and GPT-3 are really good concrete examples of this. And if you ever end up doing any natural language processing, any NLP, you'll have to deal with these sorts of problems. So a bit of an introduction to the distributed computer is what we're going to do. And I'm going to sort of basically walk through a Google Colab notebook that I've written that uses the distributed computer. And you may have heard of MNIST, you may have heard of SciFar, and maybe you've done some of this during the QMind camp. But I'm going to focus on SciFar because MNIST is a little overdone. SciFar is kind of fun. Basically, the idea is that there's a classification problem. We have 10 classes and a whole bunch of images, and we're going to try to classify these images based off of their class. Now, the way we're going to do that is we're going to use a convolutional neural network. I'm not going to go into detail as to what a convolutional neural network is. All you need to know basically is that we can feed it some inputs and we'll receive some output at the end. This is an example from AlexNet, an old network from, I want to say, the early 2000s. So we'll be using something similar to this, but many of these networks, when they take an approach to it, don't do what I call a fully convolutional neural network. So this is usually, you'll see, a bunch of convolutions. At the very end, we'll flatten and use some dense neural networks. Instead, what we'll do is we'll take fully convolutional approach until we get to the end where we'll do a global average pooling, which will allow us to take any number of sizes of image and makes our network a little bit more robust to the images that we get. And first, you're going to ask me, why would I want to do SciFar in a distributed manner? What's the point of that? I'm not going to go through training of SciFar in a distributed manner because that would take quite some time and it would have to go through a lot of understanding of what a gradient is, how to collect gradients, and how to apply gradients to weights and all that. Instead, I'll give you a simple example. Essentially, we're going to be publishing a trained model as a module to DCP, to the distributed computer, and we'll do inferencing on this specific model. So we'll do this inferencing in a distributed manner. And you might ask, what is the point of doing this? And I'll give a simple example. You've written this fantastic, killer app that uses this neural network that you've built, and it's a fantastic idea that you've got. And you publish your app. You maybe start up an AWS instance. You throw on your server, and you figure out all the inferencing needs that you have and all the requests and all this. And then overnight, you become a success. In fact, to the point where millions of people are now using your app. Well, obviously, your EC2 instance is going to crash because it's not going to be able to take in all of those requests. And so you'll need to be able to do what they call load balancing. And load balancing is essentially based off of a huge number of requests. You'll have a huge number of EC2 instances, each with your server. You'll need to give out the requests to the right computers. And maybe you don't want to do this because you're not a systems engineer. You'll pay Amazon, a few $1,000s or whatever it is to get them to do it. And it can get quite complicated to do this. And Google does it amazingly and Amazon do it amazingly. But it does take quite a level of knowledge to be able to do this. Well, DCP actually makes it so that you don't have to do this at all, because all you have to do is write a worker function, which takes a set of inputs and returns a set of outputs and performs some sort of transformation on those inputs. We take care of distributing that out. So wherever you publish out your work, wherever your app ends up, submitting the data and asking for the work to be done, we will pass it off to our scheduler, and our scheduler will do this sort of load balancing for you, and we'll return the results to the right client. That makes it really easy for you to essentially publish out your modules and do this distributed inferencing as easily as possible. So before I continue, I'm going to go ahead and ask if Dan is online.
I am on the line. How are you doing, everyone? Excellent. So just a few quick words about Distributed Compute Labs. It's an educational nonprofit that is essentially making this technology available to universities and high schools in Canada for free. So my name's Dan. I'm the executive director of this educational nonprofit. Trained as a scientist, as a physicist specifically, and totally believe in giving tools to researchers and students so that they can make their visions become reality easier with no difficulties, and especially not at huge costs that you might incur if you pull out your wallet to spend on a lot of the commercial cloud providers. We're very lucky to have Hamid on the team, and he's totally taking the AI piece all the way past the finish line with Distributed Compute Labs. And the whole point is to empower all of you folks to be able to build your killer apps and make it easy. So what we're doing at Queen's is we're turning every computer one by one into a node in this distributed on-campus supercomputer at Queen's. And we're going to be able to turn around and provide that power to all of you to power your training, your inferencing, and all the models and all the things you can do with the distributed computer. So I don't want to steal any more of Hamid's thunder. So on that, Hamid, back over to you.
Thank you, Dan. Let me go ahead and share one more time. I think I got that right. So I have this link to a collab. I'm not sure if I'll be able to, I can't seem to put it in the chat, but if one of the members, I think Ian may have a link for it. So Ian, if you could put it in the chat, that would be amazing. But basically, we're going to go through a small example here. Let's see if, can everybody see this?
Yes,
Hello?
we can see it. We can
Perfect.
see it.
Thank you. Okay, so I'm going to go ahead and start running this. Of course, Collab really doesn't like it when you aren't from Google and you try to share a link out. But I'll go ahead and start this off. So if you've ever used Collab, it's essentially a collaborative notebook. If you've ever used Jupyter Notebooks, they're essentially a good way to easily run a bunch of test code you want to try out and experiment with different models and experiment with different methods. One of the first things I usually tend to do is I go into runtime, I click on accelerator, and I try to change the runtime to a GPU accelerator. They of course have TPUs as well that they give out for free. This is entirely for free. It's all done so that Google can basically steal your great ideas, I'm sure, or something similar to that. But we'll begin with this simple sci-fi example. So, we're going to import the typical NumPy, TensorFlow, Matplotlib. And then we're going to do something a little interesting here. We're going to import this TensorFlow.js. This is a TensorFlow.js module, is a Python module that is provided by the TensorFlow team at Google. You can install it just by running this. And essentially, it allows you to convert your Python model into a TensorFlow.js module. Now, why do we want to do this? Well, like we mentioned earlier, the distributed computer is a web protocol, so it's a web stack that we have, and so we actually end up using JavaScript internally to be able to run all of the code that you need for inferencing, for training, or whatever it may be on this cloud. That makes it really nice and easy to distribute out the code because the web is built for portability and a distributed aspect of it. And so it makes it really easy to package up the dependencies as well and submit it out to all of the workers that may need it. We're also going to go ahead and import TF-Keras datasets CIFAR 10. So like I said, CIFAR 10 is the dataset that has the images specifically for the 10 classes, frog, airplane, whatever. And we're going to normalize our input sets by dividing by 255. This makes it so that normal images are between 0 and 255. And so we're going to make them between 0 and 1. So by turning it to float 32, that gives us a little bit more range. When we divide by 255, the numbers are going to be properly between 0 and 1. I'm not going to talk too much about what two categorical means, but essentially, if you're interested, you can look up what one-hot arrays are. We have this array here that says, if, for example, we have these 10 classes, you might say that frog is class number 2 or airplane is class number 7. So you would have a whole bunch of stuff that looks like this, 7, 2, 3, 4, whatever, ... We're going to turn those into essentially arrays of arrays where the index specifically is the one that is one hot, essentially. So the 7th index would be 1, the 2nd index would be 1, et cetera, et cetera. So we're going to do this for both the train and testing, and you'll notice I'm doing this weird underscore thing before the variables. There's a reason for it. We're not going to talk about it right now, but I'll talk about it later. And I'm going to do something that you may not have seen before. I'm going to actually, so when I import this, when I'm going to build this classifier, I'm going to actually subclass TF-Keras models. So what that means is I can make a full class with, kind of like in PyTorch, with all of the functions that I need for it to do. And we're going to invoke the superclass, make sure that all of that is initialized, get the number of classes that we need, and then we're going to initialize all of our layers. So we're going to start with the convolution with 32 filters, a kernel 3 by 3, and a stride of 2, a padding of same, and a ReLU activation. You don't need to worry about what all those are. But essentially, we're going to go through, and because we're computer scientists, we like powers of 2. So we're going to keep going up by powers of 2. So 32, 64, 128. Then we're going to do this global average pooling. So at this point here, we're going to have something that looks like some batch size, some height, some width, and some number of channels, which is 128. And after this global average pooling, we're actually going to end up with something that looks like batch size 1, 1, 128. And that means that we can flatten that and go ahead and just apply the dense layer. Now we're not going to actually do the flattening because it's implied. And we're going to do this dropout. Don't worry about what that is. And the final layer is going to be the number of classes. So this final layer is going to look like batch size 10. And because we've activated it with a softmax, which if you're familiar with the softmax, makes it so that all the numbers add up to 1. We can actually treat this tensor here as being the probability of being a specific class. So if, for example, I was given a tensor whose values were, to make it easy, 0, 0, 0, 0, 0.5, 0, 0.3, 0.2, then we would know that it is more probable that it is this class than that it is, this class or that class or any of the other classes. And we're going to define the typical behavior when we call a specific input on it is just to run through all of our layers and apply that layer. So this is all basic Python with some TensorFlow magic thrown in, and we're going to let that do its job. And basically, we're just going to compile it with a loss that is categorical cross entropy and some sort of metric based on accuracy. We're going to let it train with a specific batch size, certain number of epochs, and I like to make it stop if it ends up being not that great, and some validation so that we can go through and get some numbers based off of something that isn't our training set, because it's easy to look good on your training set. It's more important to look good on your validation. So we're going to get these numbers here, and your validation accuracy is a percentage. So 31% accurate, 41% accurate, et cetera, et cetera. It's going to keep going up. Now I'm going to let that run, but I'll go ahead and continue through this. And we're going to essentially plot out our loss as well as our accuracies over time. You can see I've already run this before, but I'll let that finish up. And voila. So we have our loss here. It's continuously decreasing. I could probably increase the number of epochs, quite honestly, and still get some improvements. And same thing here for the accuracy. It seems that the accuracy is still increasing. So we could probably increase the number of epochs. We're not going to do that right now because it's just an example. So we have a trained model here that has, between 0.5 and 0.6% accuracy, or 0.5 and 0.6 accuracy. So about 50 to 60% accurate. So now actually starts the distributed compute protocol part of this. And we're going to go ahead and upload these things called keys. You don't need to worry about too much what these are, but essentially they allow us to tell the distributed computer who we are and where we would like it to take compute credits from. So there is this concept of compute credits, which are essentially used to allow you to be able to compute. And by providing compute, you actually gain compute credits. And then you can use those compute credits to distribute out your jobs. And then we're going to go ahead and install this TensorFlow.js utility tool here, which essentially allows us to take our model, convert it to a TensorFlow.js model, and publish it to the distributed computer as a package. So I'm going to go ahead and let that run, but I'm going to also run this here, and we'll let that go. Are there any questions? Not yet? Cool. So as you can see, it's writing out the model weights and it's distributed, and you can see it's published the model at this specific location. Now this is important because we're going to use that later on. And essentially we're going to do this crazy thing here where we're going to install this library called Pixie Dust. Pixie Dust node allows Python backend in Jupyter to talk to a node backend on that same machine. Now we've installed Node already on this instance, and we've now installed Pixie Dust Node. And now what we can do is actually import Pixie Dust Node and do this npm install that you might do on a typical, Node sort of application. And this is going to install the DCP client, which actually allows you to distribute out your work. And I'm going to go ahead and set up some parameters here. So the scheduler that I'm going to use is the demo scheduler. Now, if everybody can do me a favor and go to dcp.work/demo. So that would just be a link that you can go to. And you'll see some sort of websites that has sort of the distributed computer, DCP demo worker, click to start to connect to the demo scheduler. Just go ahead and press start there. And you'll notice that it's going to start essentially looking for work to do. And essentially what you've done is you've spun up a new distributed worker to actually act on this specific cluster. And we're going to go ahead and, yep, okay, so we've cleared out the context for node. And we're going to initialize all of our DCP stuff. It's only a few lines of code, less than 14, 15 lines of code here to get initialized. And something interesting is that before we had all these underscores before our Python variables. Well, the reason we did that is because Pixie Dust Node has this interesting implementation that I've written into it that allows you to essentially pass variables from the Python end to the Node end quite easily. So this is a NumPy array that I'm going to take the first 100 elements or so, and I'm going to go ahead and let it print out the first element in the Python sample. As you can see, it's 0.619, and this is just information about the inputs here. And I've written this main function which takes those 100 samples and is going to create this submission array. I'm going to print out the first element in JavaScript as well. And you can tell that this is a node cell because I've got this %% node here. And I'm also going to initialize this results array here. And basically, we're just going to push in each of the slices into this array, submit it out using this syntax here. This is all you need to write to tell the workers what you're actually going to be doing. So in this case, it's going to compute.for is going to distribute out this submissions array out to each of the workers, and they're going to take that data and they're going to do some work on it and return something. What they're going to do is they're going to create these tensors, they're going to predict using your model, and they're going to calculate the accuracy, and we're just going to return that accuracy out. And I have some event emitters here just so we can listen in when the job is accepted, when we get results, and when we do some console outputs. And our job has some dependencies, so we're going to require TensorFlow, TFJS, and we're going to require that module that we published just earlier, DCP Sci-Fi 10X, and we're going to name it something, and this await job exec is actually going to execute the job, and then we're going to get our results back. So I'm going to run this, and if you have workers that are running on that dcp.work/demo, you are going to start receiving slices of that work. And as you can see, the first element in JavaScript was 0.619. And the first element in Python was also 0.619. So these are, in fact, the same variable that was shared between the Python and Node backends. And yep.
I think we have a question in the chat. Someone raised their hand. Ryan, do you have a question? Or is it an accident? No? All right, never mind then.
All good. So as you can see, we've already distributed out all 100 of our slices, and we've actually started getting some compute results in. The status here is telling us that we've started, getting those results in. And actually, I'll scroll down to the bottom here. We're already 80–90% of the way through. It shouldn't take much longer. And if you've done work, you should see those results coming through, and maybe it'll say, how many credits you've actually done. And I'm going to go ahead and stop this just so we can continue for the purposes of this demo. And as you can see here, we can, since we got some of those results in and we pushed it onto this Sci-Fi results array, we can actually just, because this array is either 0 or 1 for 0 accurate because you didn't get it accurate, or 1 because you properly predicted. And we divide by the number of results that we got back. Our accuracy on the distributed 100 sample set is 68%. So that's a very simple example where we distributed out our job and got results back very quickly. And as a simple example, you can take with you to actually try and publish a module on DCP and try to get some simple inferencing models published so that you can easily distribute out your app, compute in a way that is cost efficient and honestly a lot easier to do than setting up a whole bunch of Amazon EC2 instances. So I'm almost done. I'm going to go ahead and finish. I think I've got a few more slides just to finish up. But what's next? So essentially what's going to happen is this is just the start of our collaboration with QMinds, and the start of your introduction to the distributed compute labs and the AI task force. So if you would like to be a part of the distributed computer and our community, it is, at no cost, beta access for QMind members to be able to start this. We're going to be hosting a hands-on workshop on how to get started. The date is TBA, but you should get an email sometime in the next week. And we would like to support more projects that would like to use the distributed computer. So if you have any cool, neat ideas, I would love to talk to you about them and help you get started on the distributed computer. And we'll be hosting a variety of challenges, tasks, talks, and other events throughout the academic year. So feel free to listen up if you're interested in distributed compute in general, whether that be in AI, ML, or just in general. We'd love to hear from you and see you at these events. Perfect, thank you. I think that is everything from me.
Great,
do you have any questions?
Yeah, guys, do you have any questions? You can just unmute yourself, or you can raise your hand, I'll call on you, or you can just send them in the chat. Michael, you have a question?
Yeah, so I was wondering, let's say I have an app and I want to use the DCL for it. Considering you're setting it to random nodes, how do you protect my intellectual property and my users' privacy?
For sure. So, oh, I think someone has some echo. Okay, perfect. Okay, so essentially, we're using the JavaScript web stack, which means that we get a lot of the inherent protections that the JavaScript web sandbox provides. But let's say you're hosting it on a literal like hostile JavaScript node, let's assume. There's a variety of things you can do as the holder of that intellectual property to protect yourself from a hostile worker. And we're doing a lot of work on this. Essentially, there's this concept of homomorphic encryption, where you can take a series of weights, encrypt them using public-private keys, and you can actually perform math on this in such a way that the results are completely encrypted, and even the input sets are completely encrypted, and even your weights are completely encrypted. And so when you get the results back using your public key or private key or whatever, you can decrypt out the results and get the proper results, and do, all of your IP would be protected on this hostile node in such a way that it is, to put it as the papers would put it, cryptographically informational security wise protected. So you could even be running on a hostile scheduler with a hostile worker, and there is absolutely no way that using homomorphic encryption, the worker could somehow retrieve your results. Now, of course, homomorphic encryption isn't, we haven't tested out the machine learning or neural networks approach for homomorphic encryption, but it is something that is in our horizon and that we are approaching. We actually have a homomorphic library that works on the distributed computer today, that is available for use. So that's definitely something we're keeping in mind.
Great, thanks.
For sure.
Does anyone else have any questions they'd like to ask?
I'll quickly jump in just with an additional technique or thing that we can do with the distributed computer. We're also working with a concept called compute groups. So it's also possible for you to walk into a lab, spin up a bunch of workers, group them as part of a cluster, and then you could emit jobs that will only go to that cluster. So if you want to send a job out to the entire world, you can do that using homomorphic encryption techniques, but you can also group clusters of known and trusted workers and send work to just them. So that there's those two approaches.